Milking it with differential equations. A bottle of milk is taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius, and t is the number of minutes since the bottle was placed in the pan. M satisfies the differential equation dm dt is equal to 1/4 40 minus m. At time t equals 0, temperature of the milk is 5 degrees Celsius. It can be shown that m of t is less than 40 for all values of t. The slope field for the differential equation is shown below, and here I've sketched the solution curve starting at the point 0.05. Use the tangent line to the graph m at t equals 0 to approximate m of 2, the temperature of the milk, at t equals 2 minutes. Drawing in the tangent line here starting at the point 0.05, and using that tangent line to approximate the value at t equals 2, the first thing we notice is that the differential equation, when evaluated at t equals 0, will give us the slope of the tangent line that we're interested in. So here, dm dt evaluated at t equals 0 will equal the slope of our tangent line, which is going to be 10. Now 10 being the slope is also the rate of change in degrees Celsius per minute. Y equals mx plus b, or mt plus b here, would be y equals 10t plus b. B is going to be our vertical intercept, the y-intercept, or maybe the m-intercept. So our function here, m of t, can be modeled with our tangent line 10t plus 5, because 5 is the vertical intercept. Now using this to approximate at t equals 2 minutes, we get 25 degrees Celsius. Write an expression for the second derivative of m in terms of m. So that means we're going to take the derivative of the derivative that we have already, the second derivative. d by dt of 1/4 40 minus m will give us 1/4 times negative dm dt. Now the second derivative is negative here. Gathering some information from our problem, since m of t is always less than 40 at all times t, dm dt is greater than 0, and we can also note that they tell us that m of t is an increasing function, all things that our graph would agree with. So d2m by dt squared, or the second derivative, is negative, therefore it is less than 0. This indicates that our function is concave down. It is increasing at a decreasing rate. So that makes m of 2 equals 25 degrees, an overestimate. Now, using the separation of variables method, we want to find an expression for m of t and the particular solution of the differential equation that we were given, with the initial condition of m of 0 is 5, which is our vertical intercept. We want to separate out the variables of m and t to different sides of the equation, and then apply integration on both sides of the equation. Here we're going to have to use a u substitution. We'll let u equal 40 minus m. And from this, we'll get negative integral of du over u equals 1/4 times t plus some integration constant. We can move that negative to the other side and solve that integral as the natural log of 40 minus m. Then, exponentiating both sides of that equation, we get 40 minus m is equal to e to the negative t over 4 plus a constant, which we can rewrite as a new constant, e to the negative t over 4. So our function solving for m is 40 minus a constant times e to the negative t over 4. And plugging in t equals 0, we know that that'll give us a value of 5. So substituting that into our equation, we found that arbitrary constant here, now not so arbitrary, it is equal to 35. So now, substituting that back into our equation, we have our particular solution, m of t is equal to 40 minus 35 e to the negative t over 4 power. And that is the red curve we have graphed below. I hope you liked this question, and I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.